So far, what we have seen is that given a data set, which is either a regression problem or a classification problem, we can build a model. We can take the input data X, input variables X, and the output variable Y, and train a model that takes these input variables X as input and makes a prediction Y. Now, how did we evaluate the model? What we did was we first trained the model using the data set, all rows, and then we evaluate the model using the same input variables to see how the model does. This is unfair because I could train a model that exactly fits my data set. I can design a big neural network, train it for a really, really long time, and then get 100% accuracy or almost zero MAE on my input data set, right? So what is the catch? Also, in real world, when we build a AI model or a neural network model to make predictions, we do not have the correct labels to evaluate the model once the prediction has been made. Here's an example. Say, for example, our class works for Domino's, and what they would like to do is build a model that predicts how many customers will show up tomorrow for a particular store. So as inputs, they have the number of customers in the previous day, the temperature for tomorrow, and many other input data for tomorrow. For example, in addition, say the time, the day of the week, the time of the year, the number of sales in the previous year. And so we have all of these input variables that we have as input. Now, what we have to do is predict the number of customers for tomorrow. To train a model, say we collected data from the past 5 years, and then we have all of these rows, and we also have the actual labels for the last 5 years. That is, how many customers actually showed up on that particular day. So we can train a model, and then once the model is ready, what we finally want to do is use that model to make predictions in situations where we don't actually have the true label. That is, we will not know actually how many customers will show up tomorrow, but we want to make a prediction. Now, we can always build a model and try to build a model that actually does awesome on all the data set that we had for 5 years. So I can take all of these 5 years data and train a model that gives me 100% accuracy or zero MAE on the 5-year data set. But now the question is, if I build a model that does so well on the 5-year data set and makes a perfect prediction, can we guarantee that the model is also going to do well on this new problem for which we don't have the answer? The answer is that we don't know. So we might build a model that does very well on this 5-year data set, but it may not actually do as well on the new data set. But when designing this model, when training this model and delivering this model to Domino's, we want to give a certainty or a guarantee that our model works, right? So how do we do that? The best way to do that so far in machine learning is, even when we know these 5 years worth of data, which is, say, for example, 350 times 5 number of rows, more than 1,500 or so rows, what we can do is pretend like we don't know some of these data sets. So maybe even though we had records for the last 5 years, let's say we only knew what happened for the 4.5 years before, and then let's assume that for the last 6 months, we didn't have the true labels. So what we're going to do is split our entire data into 2 sets, the first 4.5 years, and then the last 6 months. And then we take the first 4.5 years worth of data, build a model, AI model, neural network model, and then check how it does on the last 6 months data. Now, on this data for which we actually hide the true labels, so these Y values for the 6 months data is hidden, that is, we do not, we assume that it doesn't exist. So we take the first 4.5 years of data as input X, and then the corresponding Y as the true labels, build a model out of it, and then from this model, we make predictions on the last 6 months of data, and then evaluate how it does. In other words, These 6 months data become our calibration to tune or to check how our model is. Because we know that our model can do really well on the 4.5 years. I can keep training it, I can design a big neural network model, and I can do as many things I know about neural networks to make it perform very well on the 4.5 years worth of data. Now, this places us in the context to explain what overfitting is and what generalization is. Overfitting is an issue in machine learning when we train a model so much, so well, that it does very well on the training set, but it doesn't do so well on the test set or the validation set. That's overfitting. What happens in overfitting is you either have a very big network or you have trained so long that your model starts memorizing the data points. Instead of learning patterns or patches or common patterns among groups of data, it starts thinking, well, if I have this particular number, and this particular number in these variables, this is what I have to predict. When a model starts doing that, that's not good. It's starting to memorize the data instead of looking for patterns, searching for patterns. So for that reason, we do not want our model to overfit. We want to stop the training before overfitting happens. And the way we do this is by checking how the model is doing on the validation set during the training. So we can, as we train, we can check, is my model already starting to perform poorly on the test set? If it's performing poorly on the test set, we stop the training. Now, on the opposite is the generalization. Generalization means training a model to the point when it has generalized all the patterns, all the informing patches in the data set so that it does well on the training set, but also well on the validation set. So if we trained further, it may do better on the training set, but it will start performing poorly on the validation set. So we say that a model has generalized very well if its performance on the validation set, that is the most recent 6 months, is similar to its performance for the last 4.5 years. So that's the difference between overfitting and generalization. Now we also have underfitting. So what underfitting is because of the fear of overfitting, we may just train the model only 1 or 2 epochs, or we might design a very tiny model that cannot even learn any patches or any patterns in the data. Such a model is an underfit model. So we also want to avoid underfit, because underfit simply means that we either didn't design a big enough model or we didn't train long enough. And to check all of this, whether we are underfitting or whether we are generalizing or whether we are overfitting, we always can use this validation set to check it. So we use the validation set. If we see that the performance or the accuracy on the training and validation set are both low, that means we are underfitting. If we continue to train, we'll observe certain accuracy on the training set and the validation set, and we may be generalizing at that point. If we train further, or if we train a bigger model, we may be doing better on the training set, but on the validation set, your performance may either stay same or start going down. So at this point, we are starting to overfit. Now, going back to the dominoes example and splitting the data set into first 4.5 years and the last 6 months, in a standard tabular data where time is not a critical decider of the output, it's always important to shuffle your data set, that is, randomize the rows before you split them. The reason being, in some data sets, all the positive labels, that is, say for example, all the smaller values or zeros are in the first set of rows, and then all the positive ones are at the bottom. In other words, say for example, if we are going to predict whether someone has diabetes or not, then maybe all the positive examples are in the first set of rows, and then the second half of the file has all the non-diabetes rows. So if we don't shuffle the data, then on the validation set, we will only have either just positive examples or only negative examples. So for that reason, when we are doing data splitting, it's extremely important that we shuffle the rows. Once again, say this is how our data looks like. We have our input variables, And then we have our output variable quality. So this is our output variable, and all of these others are input variables x. So this is our x, and this is our y. Now remember, in future, we will have x, but not y. So after we deploy the model, we are not going to have y with us. So this is the data that's available to us. What we want to do is split the data for training and validation. So from this x, we want to obtain x train, and we want to obtain x valid. And from this y, we want to obtain y train and y valid. So this becomes our validation set, and this becomes our training set. We will use both X train and Y train to perform the training, but we will use X valid as input to make predictions on a trained model and then evaluate using Y valid. So this is like a test for the model, an exam for the model to see how it's doing. If it's not doing very well, we can go back and train the model again using X train and Y train. Now in Python, we can do this in the following way. If I want to select 70% of these examples as the training set, that is, I want 70% of my data to be in the X train or training set and remaining 30% in the validation set, I can create a variable that keeps the number of items that represents 30%. So I can do 0.3 times the length of my data set, and this gives me the index of the first 30%. And then I can do the first 30% of my rows as X valid. Of course, this should be replaced by give me all columns. And Y valid is the first 30% of the rows and all columns, and similarly X train. So this is the remaining 70% because we go from 30% all the way to the end, 30% all the way to the end using this column. So this gives me my 70% of the data that I'm going to use for training and the 30% that I'm going to use to validate the model.